plus CH2 plus BH3, BH1 plus AH2 plus CH3, CH1 plus BH2 plus CH3. How did I get CH3 in both of those? That's supposed to be A. So, I mean, this can be written as A plus BJ plus CJ squared times H1 plus H2J plus H3J squared. With the understanding, of course, that one so this is really let's see if it worked. No, yeah, that'll give you one, right? There's where those three terms go to.
The same thing for everything else, yeah.
But the see that is very fortuitous that I can rewrite this matrix column product as a multiplication of algebra elements. The only reason I can do that is because this is special kind of matrix. This is a regular representative of H3. So for this one, I can't rewrite this.
No.
Well, I mean, I shouldn't be so glib. I mean, does there exist an algebra for which
that's the
regular representation of some number? I mean, I can't rule that out, but I don't know right offhand. So there's a much more difficult question. Is there an algebra for which that is a regular representative?
Couldn't tell you off the top of my head, but
Yeah, I don't know. I mean, I don't know right offhand. And that's the kind of more challenging question I'm looking at with affiliate.
Okay.
But actually not even. Well, I mean, we've got some three-dimensional stuff, but like we're really more two-dimensional. Although who knows, he may be six-dimensional. I haven't talked to him for a little while. So I want to point out, I'm trying to impress upon you how amazing it is that we can define a derivative in the calculus, which is again a function on the algebra.
yeah.
And likewise, we can define second derivatives. Like, since this is a function on the algebra, that means I can define the second derivative
On the algebra.
as a derivative of the derivative,
Yeah.
and so forth. When you study advanced calculus of several variables more deeply, what you learn is that the natural objects which you think of as the derivative is not a function again. When you look at a function from Rn to Rn, the second derivative is essentially identified with a symmetric bilinear map. So it's like essentially something that it takes in two arguments, and it's mapping from the tangent space across the tangent space to the tangent space across the tangent space. And like that continues up the chain. Like a third derivative it's a mapping from a Cartesian product of 3 copies of the tangent space to 3 copies of the tangent space. Completely symmetric because you got the, you can do that at least, but so this is so special and beautiful that we can do that here. And like I have a quote from Dudnay. I'm probably saying that wrong, but the double-fingered scrolling got me again. So here's a quote on page 19. Following quote is from Dudnay. On a one-dimensional vector space, there is a one-to-one correspondence between linear forms and numbers, and therefore the derivative at a point is defined as a number instead of a linear form. Right. Now he says this because he soon thereafter defines the derivative as a linear form instead. There's, oh man, that's not the real quote from Dudnay has a shibboleth in it. Is that it? I thought I had more of the quote in here.
No, just a one.
Yeah.
On a one-dimensional vector space, there's one-to-one correspondence between linear forms, and therefore derivative of point is defined as a number instead of a linear form.
So there we go. Now we have the derivative as a function, right?
Mm-hmm.
And so we can take theorem 5.9. So the next about 3 pages of notes have some entirely unsurprising results.
Oh, this is these are just derivative stuff.
Yeah. So like if we have 2 functions which are differentiable near p,
Mm-hmm.
their sum is also a differentiable near p.
Yep. If they're multiplicative.
So like an algebra multiple of a function.
Wait, this is. Oh, no, you're taking the derivative of the 1. Okay, yeah.
So like look at the proof. The proof is just essentially that if you have a sum of functions, their differential is the sum of the differentials.
Yep.
And if one of the differentials is right alinear and the other is right alinear, then their sum is likewise right alinear. And more than that, when you look at the actual, formula for the derivative itself, so we're looking at, dpf plus g, right?
Mm-hmm.
Of 1, that should be, that's f prime, f plus g prime would be. Well, that's exactly df p of 1 plus dg p of 1, which is f prime of p plus g prime of p. So, basically all these rules of calculus come essentially for free from just simple algebra of the regular representation paired with, results from advanced calculus.
Oh, and then we get theorem 5.10.
So you see the proof of 2 is like a little bit more interesting because it actually involves the algebra multiplication.
Yeah, but I mean, essentially it just acts like a constant.
Right. So you see that I actually calculate the.
Yeah.
I can't just refer to a result from advanced calculus because it actually involves the algebra multiplication.
Yeah.
So I define the differential as c times the differential of f,
Mm-hmm.
and then I prove that it works.
Because you multiplied it all the way through, and then
Factor out the c.
Yep. Then you get c.
And you notice that here I have to use that submultiplicity. Notice that right here, the norm of the Frechet quotient for g.
Mm-hmm.
Is equal to that by the calculation above, the norm of c times the Frechet quotient for f.
Yeah.
but we also have the submultiplicative thing for the norm, so that's less equal to the submultiplicative constant ma times the norm of c times the norm Fauché norm. But we're given that the Fauché norm goes to 0 because that is tantamount to saying that f is a differentiable.
Yeah.
So therefore, g is differentiable, and let's see here. I think I've already argued that this L is in RA, have I?
Don't remember.
Technically, I should mention that. I don't think I think I.
Oh yeah, so L V star W C star dp V star W is equal to C star
Oh!
V star W L V star W. Thus L's in right. Right.
It's hiding in plain sight, isn't
Yeah.
it? Yeah. So that's needed because that
dpg is equal to L, and then if H is unequal to 0, let f of the Frenet of f and of G denote the Fauché quotients.
so as you can see there, and then of course you feed it 1, and you get C times the derivative of f, and there it is.
Which gives you C star the Frenet of f, but by 5.1 we find that if dp of G is equal to L, therefore C star f is in CAP, and then all that should give you dpf.
Mm-hmm. So far, pretty
nicely we're getting just good calculus results.
exactly.
Like we're not straying off. And this is for general algebra, not right? For that it's in three dimensions.
This is for an n-dimensional associative algebra with unity. It even could be like so up to this point. I really need to think back and figure out what part of my some of my Cauchy-Riemann equation stuff actually does make sense for the non-commutative case. Certainly these two theorems are fine for non-commutative algebras. And in fact, theorem 5.10 is most interesting if you understand it in the context where the algebra might be non-commutative, because then there's something that special happens if it's commutative.
Yeah.
So notice that I say that the differential of the product of f and g, so notice that that's the algebra product. We're multiplying f of g according to their values in the algebra. So like that formula in the first line, that's general. Even if the algebra was not commutative, that still holds.
Okay.
But if it's commutative, in fact, what I mean to say is that formula holds. I noticed that I haven't actually said that f times g is a differentiable.
Mm.
It may or may not be in the case that the algebra is not commutative.
Mm-hmm.
However, if the algebra is commutative, then f star g is a differentiable, and its derivative is given by the natural product rule right there.
Yeah.
So let's work that out. Alright, so you look at f star g, right? Take the differential of that speed of f star g. Oh, I can't just do that though, can I? Ooh, I can't just do that. Okay. So, what do I know? I know that f of p plus h minus f of p minus dpf of h over norm h. Let's call that the Frechet quotient of f. I know that that goes to 0. And likewise, I know that g of p plus h minus g of p minus dp g of h divided by the norm of h. Let's call that the Frechet quotient of g. I know that that goes to 0 as h goes to 0, right? So here's the thing. If we look at f of p plus h times g of p plus h, right? Notice that you can solve these equations and you can expand f of p plus h in terms of its Frechet quotient.
Yeah.
And we're in a limiting process, so h is not 0, so the norm of h is not 0. It's getting close to 0, right? But that doesn't matter. So the joy of limits, right? So this is f of p plus dpf of h plus ff norm of h, right? Times the same thing, but with g. So this, of course, gives us f of p star g of p, right? Plus, well, f of p star dp g of h plus dpf of h star g of p. All right. Plus, what else? Plus, like, Frechet f times the norm h, g of times g of p plus dp g of h plus, you know, f of p plus dp f of h star Frechet g of h, right? And then, of course, plus Frechet times Frechet, and then you got your norm h squared, right?
Mm-hmm.
So, you can see then, if we look at f of p plus h times g of p plus h minus f of p star g of p minus L of h, all divided by norm h. And here L I'm going to define as this right here. Right, so I'm basically taking this minus that, right? And then I divide by h.
Okay, so
What I'm left with is this guy times g of p plus dp g of h plus f of p plus dp f of h star fg plus ff star fg norm h, right? and what happens as h goes to 0.
That term.
Yeah, this goes to 0.
Yeah.
This also goes to 0, but that goes to g of p.
Yeah.
But that's fine.
Because it's
0
0
times-
0. Yeah.
Yeah, so this term goes to 0.
That term goes that df that
The Frechet quotient of g is by assumption limiting to 0.
yeah,
So that goes to 0.
and then that goes to p, but still 0, and then those two both go to 0.
So that goes to show, hooray, this L sub h is the differential of f times f star g.
Mm-hmm.
I guess technically I need to prove that it's real linear, okay? But real linearity, so like the question is, can you replace h with, say, like c1h plus k, and then factor the c1 out and break up to h plus k? And yes, you can, because the algebra multiplication is got that distributive property which allows us to break the addition up, and the real constants we can factor out. So like real linearity of L, that is true because of the assumed linearity, real linearity of the differentials. Okay. Now, what we don't know, right, is whether or not. So so in summary, we've shown that dp of f star g exists
Mm-hmm.
in the category of real differential functions, and it is equal to f of p star dp g. So I gotta put the h here. Actually, I'm gonna put v star w.
Okay, now I see where you're at. Oh, okay.
Plus dp f of, I'm going to put v star w here instead, times gp. Now I put v star w here because I want to talk about the next thing, which is,
Yeah, the commutativity.
is this in fact write a linear map? Okay. Is this, what's in red here, does that define a right a linear map? The answer is generally no, because even though I can factor out, see, I can get started. This piece is fine. See, this piece is fine. See this? I can take that and I can multiply by w, because I can, by associativity, I can pull the w out because I got right linearity of the g, dfg, dpg. Over here, though, I'm in trouble. See, because I've got dpf of v times w, right, times gp, and I have no right in a noncommutative algebra
Flip those.
to take that and bring it over here.
Yeah.
So I'm faced with this quirky thing that,
No, I was trying to think if you remember how we can say dpf of v is dpf of v star w. But I don't think that would be able to, because
yeah, that's how we got there.
no, but I was saying maybe you could flip that, but no, that'd be commutativity on that side anyway.
Right. So there it is. In the non-commutative case, we lose the product rule.
Yeah.
Now, there have been authors, people who've constructed non-standard, what you might call theories of hypercomplex variables. This is a theory of hypercomplex. People call it hypercomplex variables because it's kind of beyond complex variables. But I just like the term because I don't think of what I'm doing as complex variables, because it may or may not cohere to the complex variables is such a beautiful and special context.
Mm-hmm.
And I don't want to say I'm doing something that's beyond that, and because it may or may not look like complex variables. It depends on what algebra you're doing,
Yeah.
But anyway, there have been authors in the past who have made a definition of differentiability under the assumption, the guiding principle, that the product rule should be part of it.
But
Yeah, so that's right. They're going to have to do something to deal with this. And if I recall correctly, I told you before, like Ward and Wagner, the two students of McDuffie, I think Ward actually had a somewhat more exotic definition of differentiability in his original paper precisely because of this issue. But in any event, here we go. I actually have an example. So I think, were you looking at my, did I just do exactly what I had in the paper?
Yeah.
It's funny, I hadn't looked in the next page.
You did 52. But
you
you did.
Oh, I had it, and I see I had not used my submultiplicativity like a good boy. See, I'd skip some steps here, technically.
Well, you assume commutativity.
So, like, I said that goes to 0, that goes to 0, that goes to 0, but, like, the proper way to do this sort of thing is to take the norm of both sides and then show, it all goes back down to the squeeze theorem. Take the norm of both sides, and then you squeeze above by something that limits to 0. So, the arguments in my paper are better than what I wrote on the board, is what I'm saying.
No. Okay.
And so if it's commutative, you see that equation 52,
Yeah.
it allows us to,
Have a product rule.
And in that case, when you feed it 1, you get f prime times g plus f times g prime, just like usual. And so let's see here, equation 55. I'm like, okay, so what is it? What do we need? So I say, okay, so all right, suppose for a second that your algebra maybe isn't differential. Your algebra isn't commutative.
Yeah.
But you want the product of f and g. So f and g are a-differentiable. What does it take for the product of f and g to still be a-differentiable, right?
Mm-hmm.
Well, somehow I need this to work out, right?
Yeah.
So we need.
What if no? Never mind.
What we need is for this. We can just focus on this, right? This is fine.
Yeah.
So we can just focus on this piece and say, well, what we need is we need d. dpf
What if W's commutative?
of v.
No, wait. DPF would have to be commutative, not W.
We need that times w times g of p to be equal to dpf of v times g of p times w, right?
Yes.
We need this for all v and w in A.
Yep.
See, that's the thing, is we don't get to pick and choose the w. Like, we have to show a linearity with respect to an arbitrary w we're pulling out. So there's that, And what do I say on that equation there? Equation 55? Well, equation 55 is just that, right?
Mm-hmm.
And I recast it by factoring out the dpf of v. See, we can see that we have it here and here, so we can just rewrite that as dpf v times what? Times w times g of p minus g of p times w, right? So this means that it can mean different things, right? But that equation we have to somehow satisfy for all w. Now, it comes some stupid stuff, right? D of p is 0, we're good to go. Right? Okay, but then this all kind of collapses down. Right, so we're definitely interested in the case that the differential of f is non-zero.
Mm-hmm.
What do I say?
Well, could you prove that middle term is 0? No, it has to be 0.
So we're in a non-commutative algebra, that isn't.
No, but if it's 0, one of these terms has to be 0. right?
If DPF is 0?
No, not if DPF is 0.
Oh, if that's 0, does one of those have to be 0? Oh no, they could be 0 divisors. Aha! Welcome to the world of not working in a field.
Yeah.
So, now, if f is constant, then DPF is 0, right? And as I point out, that was Theorem 5.9 part 2, right? I said for a less trivial example, we could seek a function g for which that isn't a 0 divisor, but it's just straight up 0, right?
Constant.
Now, you can define the center of an algebra, the center of the algebra. You remember you define the center of a group.
Yeah.
So center of an algebra, kind of the same thing. X in A such that x times y is equal to y times x.
Yeah.
For all y in A. The center forms an ideal of A. An ideal is a subset of the algebra that when you multiply that subset by the algebra, all that pops back out is that subset again.
Okay.
It sort of eats the algebra. Right.
So essentially we're finding a W that's a center or a GP that's a center.
Is that right? Does the center actually form an ideal? Or have I forgotten my definition of ideal? Huh. All right. Sorry, I set up the pool. You say A is a simple algebra if it has no ideals except for 0 and all of A. That's right. So if G of P is in the center of A and G of P is not equal to 0, then we find A is not a simple algebra. Alright, so I say another aspect of this result is the non-existence of higher than first order A polynomials. In particular, Rosenfeld shows in 39 that there are only linear A differentiable functions over simple associative or alternative algebras. So that ties into the comment I made about the quaternions the other day. Now this example right here that I'm about to show you
5.11
is an example of a algebra which is not a simple algebra. It has a non-trivial center. And in this algebra, I can define functions f and g as I did there, all right? And I can calculate their product as I do. And I can calculate the Jacobian matrices, right? As I do. Now, keep in mind that, this is definitely an example where I'm not working with the identity as the first coordinate. Right. But anyway, so here, it turns out in this example that f and g are a-differentiable and f times g is actually g. So because f times g is just straight up g, clearly it's a-differentiable again because g is... Oh, the reason I wrote down those Jacobian matrices is to prove that they're a-differentiable because you can compare the shape in 59 to the shape you see in 60 and you can see that it fits the pattern.
Yeah.
So that's just a kind of a sneaky way to show that Cauchy-Riemann equations hold. It's just manifest that they're in the regular representation. So as such, we have f, we have g, they're both a-differentiable, all right? And their product is also a-differentiable. However, here's where it gets weird. G times f is not equal to G, it's equal to something else.
Yeah.
All right, and if you look at that Jacobian, that function's Jacobian. Oh man, double finger scrolling got me again. Really, I need to start using a different PDF viewer. I'm an idiot. I stopped using Adobe, generally speaking, because it kept like wasting my time, like preparing PDFs to look at. And was like, what are you doing? I have a 3 gigahertz computer with 16 gigabytes of RAM or whatever. Why are you taking time to load a PDF?
Yeah.
It's dumb. I guess I was too lazy to put the matrix out, but I say that there is a non-zero entry in the 2-6 entry. So 2-6 would be, how is that? Row 2. I don't see that. Maybe I mean 6-2. I must mean 6-2 entry. I mean 6-2 is 1, right? Because like the 6th component of G star F is x2 plus x5. I think I should write 6-2 there, not 2-6.
H2. So G star F. You talking about the Jacobian or the actual function?
The actual, I mean the 6th component of the function is x2 plus x5, right?
Yeah.
So that will tell me what row 6 looks like in the Jacobian. Because the 6th row corresponds to derivatives of the 6th component.
Yeah.
And so if I look at row 6, column 2, that's the 6-2 component. But I have 2-6 entry. I flipped it. Dummy. That should be 6-2. And why does that matter? Look at equation 59. If we're in row 6, 6-2 is 0. Dude.
Yeah.
What? Oh. You know, I've had students read this paper before. I feel like maybe they found it and I just didn't fix it. That's probably, let's be optimistic. They found it and I didn't fix it. Let's say that's what it was. So G star F, can you tell me the formula? G star F?
On 511.
Yeah, I was like, yeah. Is what was it?
0, 0, 0, x2, 0, x2 plus x5.
Okay, so the Jacobian of G star F, what is it? It is first of all 3 rows
Of zeros.
of zeros. Then x2. Zero. Another row of zeros. And then
x2, x5. Yeah. So yeah, you do have a 6-2 position. Don't have a 2-6.
yeah, right. So
In the 6-2, and then if you change it in the 6-2 entry and
so look at 59.
Yeah. It's not 0.
So 59.
Yeah.
Oh, I see the problem. So that is 0 in 59, but it is 1.
Yeah.
Therefore, not a differentiable.
Yeah.
So we have this quirky situation in a noncommutative algebra. You can have the situation where the product one way is differentiable, but the product the other is not. So anyway, it took me a while to find this out.
No, it's just going from commutative things to non-commutative things is very interesting.
Yeah, the
Because even in abstract, we rarely dealt with things that weren't abelian also. like, we set up things that were not inherently abelian, but they were very simple cases.
So actually, this example, it's
Like sock shoes as an example.
it's partly due to probably mostly due to Robert Bryant.
Don't.
He was the president of the AMS for a year or two, a couple years ago. He's the director of the MSRI. He's I think he's a professor at Duke.
Oh, okay.
One of the more prolific people on the Math Overflow website. My advisor happened to teach him at NC State in the early 70s. He was very good even then. But anyway, because I kind of told him, how would I find an example of that? He's like, well, you just need an algebra where the left. I forget this language for it, but I was like, oh, okay, and then I talked to my brother or whatever, and then I figured out, okay, so I need something that's not simple, and it has a non-trivial center, and that led me to look at triangular matrices. You can look at like
the one the upper triangle or triangle.
Yeah, like upper.
The determinant is
Right.
the diagonal.
Right, and because if you look at triangular matrices, the product of two triangular matrices is again triangular matrix.
Yeah.
So if you had like a 4x4 triangular matrix, you'd have like 4 plus 3 plus 2.
Yeah.
I guess I probably was working with a 3x3 because the 3x3 matrix has 3 plus 2 plus 1, which is 6.
Yeah.
So 3x3 upper triangular matrices will allow you to, if you look at their product, that will allow you to define a multiplication on R6, which is not commutative because it's not the case that triangular matrices necessarily commute. So that's where this product, this mysterious R6 algebra came from. That's its source. Because if you want something that's not commutative, that you kind of have a handle on,
R6
matrices are where to go.
Yeah.
Yeah. Now, Theorem 5.12, can you recognize this one?
Okay, so U and B are contained in the algebra are open sets, then G to U to B and F of B to A are a differential functions if P is in U. Then F of G of P's. This is wait. Chain? Is it chain rule?
Yeah, it's a chain rule. And the proof of this one is really, really easy. So the chain rule in advanced calculus is just that the differential of a composite is the composite of the differentials. And when you marry that to the right linearity, as you can see in equation 61,
Yeah.
we can
Real
just
chain rule, definition of a composite.
then pull the multiplication out of the inside one.
One sec. So, yep. Okay. Yep. And then you say as G is in CAP,
Mm-hmm.
this, and this. And so you do. Oh, okay. So you take, yeah. So you can take the W out, and then and then you say as F is, so you do the same thing with that. Real chain rule.
Yeah. So there it is. Dang it, I just did it again.
But this, you don't even have to have commutativity for this one.
That's right.
That's nice. So even without, so the only thing you lose in commutativity is multiplying a function times a function.
Yeah, product rule gets into trouble for non-commutative. Chain rules.
Theorem rule stays,
Chain rules
which is
fine,
nice.
which is good. And then my next example is, if we have the nth power function in the algebra, then the derivative is n zeta to the n minus 1.
Mm-hmm.
And So I essentially just prove it by induction on the power rule.
Yep.
I mean, excuse me, on the product rule, right?
Yeah. That's the claim is true for n plus 1. We prove that you zeta, the zeta n is n for all n. Yep.
So I can write this stuff out if you want, or
No, I mean,
it's good.
I see.
Okay.
I don't see any flaws.
So this is comforting. The power rule holds for a calculus.
Oh yeah.
Yeah.
For yeah, but under the chain type of deal though. Hence IDs, hence moreover. df of p of x star y I d. We calculate that this, and we find that as star n and then g's zeta. By induction, the hypothesis we've already argued is equal. Oh, okay. Yeah, we should. Because yeah, you get
Jenny,
that
if you need
identity.
to turn the dishwasher on, that's fine. Oh.
Yeah, because you get the identity element out of the G prime.
Mm-hmm.
Cool. Power rule states.
Whoa. So then, turn the page here. I say, okay, so we're going to define f prime of zeta equal to df d zeta of zeta, which will also denote as d zeta of f of zeta. And likewise, we'll write f prime as df. So in other words, I'm going to use all the usual calculus notations with the... So...
Newtonian. Wait, was that Newtonian or was that algebraic?
So now maybe the thing I said in Theorem 6.6 makes more sense. So like partial f partial zeta can be identified as df d zeta in the context that f is adifferentiable. Now Theorem 5.14 we did last time, ironically enough.
Oh, so I see some stuff, yeah.
Mm-hmm. And there's the calculation we went through without the picture.
And then we just did these Cauchy Riemanns. So
All right.
6.7.
We're getting there, aren't we? Yep. Let's see here.
Or are we at deleted difference quotients?
Yeah, I think we just made it to, I mean, items 1, 2, and 3 on page 30. This is like, you know, like this is my long-term, I'd really like to come up with elegant ways to do this kind of thing.
Generalize A Laplace equations.
You know, like given a PDE or system of PDEs in real variables, how do you choose an algebra to convert the differential equation, partial differential equation, to a corresponding differential equation of the algebra, such that I can study it using a calculus and then track back and use the solution of the a differential equation to solve the underlying PDE.
So it's kind of like what we do for the Laplace transformations. Like we
Kind of
transform,
like that.
but you're doing it over a calculus or over an algebra, which then you do the calculus under that and then
Yeah.
pull it back.
Yeah, I mean, so if
That kind of some really cool.
I think so. If I'm so fortunate that the system of PDEs, like I have n PDEs, they're all coupled together, right? But if that coupling was actually an algebra multiplication disguise or something, there's hope that I could take that system of n coupled PDEs and convert it to a single uncoupled algebra differential equation, which I could solve essentially in the style of calculus 1 or 2. And then track back and see solutions. But
That'd be big.
yeah, the flip side of this is I can invent weird partial differential equations on the basis of, like, there's another way to use this technology, which is it's just slightly less, I guess you could say, ethical.
Oh, like invented an algebra that makes those partial differential equations very nice.
Or ugly. So you could take the algebra, which is ugly, and make correspondingly ugly partial differential equations, and then you could somehow, oh my goodness, I know all these fascinating properties of these complicated partial differential equations. But you don't tell your audience that you know the man behind the curtain is the 6 hyperbolic numbers cross the 3 null numbers or whatever.
Yeah.
But because you know that, you know the entire structure theorem of the functions that are solutions to the thing.
Oh, so you make it seem like it's okay.
You would have complete control over the calculus.
Yeah.
But if you write it in real notation, it would just seem impossible to solve, and yet you would have authority knowing exactly what's going on.
So that's nice as a like a power move. I think, I mean, if we could find an algebra that, I don't know, but wouldn't you have to find like PDEs that are like kind of like, could you find any given PDE, or would you do it as in, would you only like want to study PDEs that are hot topic PDEs and find an algebra that would work?
I mean,
with
it's
those? And with those, like, would it only be PDEs that are in R, or like R cross R? Like, are there PDEs are there any PDEs that aren't like in other algebras that aren't complex?
your imagination's the only limit.
No.
I mean, I have used this technology to invent homework exercises for advanced calculus.
Mm-hmm.
I've been able to make some kind of like really painful problems that I could solve easily. So on that scale of things, it's been useful, but I'm just joking. So on the one hand, I'm joking.
Yeah.
On the other hand, that might actually unlock some conceptual doors doing that. Like it might be worthwhile doing, but so I'll try to go really, really fast through this next section, the deleted difference quotient section. So you're looking at definition 7.1?
Yeah.
All right, so let be a function from like a domain, let's say an open subset of the algebra to the algebra again.
Mm-hmm.
All right. And P is a point in that domain. Number 1, if f is a differentiable at P, then f is d1 at P. So what I'm saying is d1 is the definition of a differentiable that I have already shared with you today, previous day, and will continue to use. All right. For the purposes of this section only, if the limit as a is in the group of units, I mean zeta is in the group of units approaches P, of the difference quotient f of zeta minus f of P over zeta minus P, if that exists, then f is d2 at P. All right.
What does that mean?
That means it's d2 at P. This is the definition.
But what does the D1 mean? D2?
A differentiable.
Oh, okay. That's
So, I mean, what I'm doing is D1 is a differentiability as characterized by right linearity of the differential.
Okay.
And really the Fouché quotient, all right? D2 differentiability at P is a differentiability as captured by the deleted difference quotient. It's a deleted difference quotient because you're dividing by vectors, but you're only dividing by the vectors for which the multiplicative inverse exists in the algebra. So it's okay. I mean, that actually is okay. It's a legitimate limit that you can take. It's because the thing is the group of units is dense in the algebra, so it makes sense to take a limit in a dense set like that. But in this section, I compare and contrast these two notions of differentiability. All right.
Mm-hmm. So P exists, F is D2. Okay.
So let's see here. I look at the Dirichlet function in the spirit of Dirichlet, actually. I say it's 0 if it's either 0 or a unit, and it's 1 if it's a zero divisor, a non-zero zero divisor. So in this case, I get the difference quotient is 0, like straight up 0 for all for all zeta in the units. So that means that it is deleted difference quotient. It's D2 differentiable over A and also at P equals 0. But on the other hand, A differentiability, in other words, D1 differentiability implies real differentiability and thus continuity. Clearly F is not continuous at P equal to 0. Thus F is not D1 differentiable at P equal to 0. See, because the notion of differentiability that we have shared today implies real differentiability, and real differentiability implies continuity. The deleted difference quotient definition, on the other hand, does not. Well, sounds okay. Sometimes you have to wait it out. All right, so Theorem 7.3. If it's D2 differentiable, then this deleted Frechet limit is 0. All right.
Frechet limit. Okay, so yep.
So there's that.
And
And
then
then-
the term comes back. Okay.
Let's see here. Come on. I lost my place. Alright, so then next up I have theorem 7.4. If f is a function of a which is continuous on some open set containing zeta naught, then if f is d2 differentiable at zeta naught, then f1 is d1 differentiable at zeta naught. So basically this is kind of an antidote to the Dirichlet example. If you throw in continuity in addition to D2 differentiability at a point, that is enough to get D1 differentiability at that point.
Well, D1 just implies that it just needs continuity over the real, right?
D1 is that basically that the function is real differentiable and that the differential is in fact right alinear. Now, Theorem 7.5 says if you have an open set and if f is d2 at each point mu, then f is continuous on u. So now I'm saying, well, if you actually have the deleted difference quotient differentiability at each point in an open set, then you get continuity. That's a little bit slippery. Right? Usually if we have differentiability at a point, it implies continuity at a point.
Yeah.
Now I'm saying D2 differentiability on an open set implies continuity on that open set. That is a pretty significant weakening of the usual result. And I say, okay, so given theorem 7.5 and 7.4, we obtain the main result of this section. Let U be an open set in A. If f is D2 at each point mu, then f is D1 on U. In other words, functions which are D2 holomorphic are necessarily D1 holomorphic. The term holomorphic means it's differentiable on an open set. So